This is Dr. Hibbs speaking. I have with me this afternoon a conservation class from Ball State University to tour the sewage treatment plant here at the city of Muncie. Our guide for the tour this afternoon has his bachelor's degree from Indiana State. Later he completed his master's degree from Massachusetts Institute of Technology, and for many years was a science teacher at Muncie Central High School. At this time, I'd like to introduce Mr. Zederberg, Chief Chemist of the sewage treatment plant.
You come today to visit the treatment plant for sewage for the city of Muncie. We more nearly today call, or more frequently call, sewage polluted water, since that takes in industrial waste as well as the sanitary waste from the home. If we go back to the beginning of this, we have the solid and liquid waste from human bodies in the homes, in the bathroom in particular. We have the waste from the kitchen, the natural waste. We have the disposals, which are added to grind up the garbage. All of that goes in the sewer. In addition to this, we have certain industrial waste. Industry sometimes gives a plant such as this as much or more of a load than the sanitary waste from homes. And then in addition to that, we very frequently have in the older parts of the cities, and that is true of Muncie, it's true of Kokomo, it's true of Indianapolis, it's true of all the larger cities. They had only one sewer system at one time. And that sewer system carried everything, the runoff water and the sanitary waste and the industrial waste, to the nearest watershed system. So we have rainwater also going into these main sewers. So coming to us, we have quite a variety of materials. Essentially, the sanitary waste, the waste from the home, industrial waste, waste from industry, and then the runoff water from the streets, which contain a good deal of sand and gravel and sticks and variety of things when we have a heavy shower. And that is what this plant treats. Now, in the outlying areas of Muncie, and that's true of other cities, they're required now to put in two separate sewer systems. When in addition goes that, they've got to put in a relatively small sewer to bring sanitary waste from the home and such waste from industry as might exist in these newly organized areas to a treatment plant such as this. And then they put in a much larger one, and perhaps several of them, to carry the runoff water from the streets to the nearest watershed system. That may be White River, or Killbuck, or Buck Creek in the case of Muncie. But it would cost millions and millions of dollars to go in downtown Muncie and tear up the streets and put in two separate sewer systems where there is only one big sewer at the present time. Now, the map that you see on the wall there has quite a number of red lines on it. That's the city of Muncie in the outlying area. Those red lines are proposed new sewers to be added in the next some 10 years. Now, probably some of them won't be added because they can find means of doubling up on some of these, but essentially that is an advanced program. Now, whether this plant can treat all of that area or not, it is somewhat questionable. This plant was built and put in service in 1941 and was built to take care of 7.5 million gallons in a 24-hour period. Almost as soon as it was built, and this same thing has been true of practically every sewage treatment plant that's been built, it was undersized, and we were trying to put 8, 9, 10, 11, 12 million gallons through a plant built for 7.5 million. Now, in Indiana, we have State Board of Health, as every state has, and it's the purpose of this State Board of Health to look after the health problems in general of all of the inhabitants of the state. And one division of this State Board of Health is the State Stream Pollution Control Board. And it's their purpose to analyze or have analyzed samples from the various streams or effluents from plants such as this to check to see what degree of pollution, how much pollution is entering the streams of Indiana. And if they find that Muncie, for instance, is polluting White River beyond a certain point, they bring pressure to bear on us to clean up that polluted material. And they cited us for polluting White River in 1946. A city that has elected officials, the mayor and council and so on, by the time you get one set of officers just about ready to act on something like this, then the political scene changes and they go over to the other political party, and you got to start working all the way through again, and maybe 2 or 3 such administrations before you have a group that acts rapidly enough that before they get out of office they have a bond issue left. So it was some 10 years before this plant was enlarged. And in 1957, it was tripled in size after about 3 years of construction effort. It can now take care of 20 million gallons complete treatment and an additional 10 million gallons of partial treatment, up to and including the primary treatment, which I'll explain to you later. Anything above this 30 million gallons is diverted to the river, either here at the plant or when the sewer gets full as it comes down through Muncie with stormwater and sanitary sewage. There are spillovers that take the excess into the river. So we do send some raw sewage to the river when we have heavy rainfall. But the river is up then, has extra supply of oxygen, and that's not so bad because it can oxidize the impurities. Right now, when the river is very low, it'd be very unfortunate if we had very much sewage. The sewer that brings the sewage to this plant is 5 feet in diameter. There is only one that comes down to the plant. A lot of laterals that hook on in Muncie, of course. It's capable of bringing 42.5 million gallons of sewage to this plant in a 24-hour period. Very questionable whether this plant can be enlarged to take care of that much sewage, since we have a rather limited area of ground here. Flows by gravity, that is just downhill, just like water in the river flows downhill until it reaches the plant. First thing that happens to it here, it is screened to remove large pieces of material such as tree limbs, tubiphores, rags, and so forth, such as that. And it's screened by having bars of iron that are about 2 inches apart, several of these, spaced and angling down into the flowing sewage. And here is where we get the accumulation of those large obstruction pieces of material. Every so often there are rakes that come up over these bars, just like my right hand represents a rake, my left hand the bars of iron, and brings up high enough to be removed the accumulated material. Since this is mostly combustible and waste material, it's taken to the back end of the lot and burned. We do get a good deal of grease sometimes coming up with the oil, with the rags and other waste material, and it is burned likewise. The sewage then goes in an underground concrete tank, which we call a wet well. It simply is a place to hold it until our pumps can pick it up. Our pumps are centrifugal in action. That is, they give a whirl to the liquid, and the only outlet after they get in the pump line is to go up, and it lifts it about 30 feet high. This is the highest point in the plant, and from this highest point the liquid flows by gravity through all of our tanks until it becomes the effluent of the plant and is out in the river. Now I'll talk about influent and effluent. Influent is in means in, and fluo means to flow. It means the liquid that's flowing into a plant. Effluent, F means out of, and flowing out. We have influent into tanks and effluent out of tanks, and influent into the whole plant and effluent of the whole plant. The highest point in the plant is called the detritor, D-E-T-R-I-T-O-R. The detritor is a grit removal device. There are 2 such tanks, and they are about as long as this room is long and about the same width as the room is long. The liquid in them is about 3.5 feet in depth. Comes in gushing on one side across the weir under the lifting power of the pumps, and it flows fast enough that it keeps suspended organic waste, human excrement and waste from disposals and certain industrial waste and so on. We want the organic material to be kept suspended to go over the weir and to the next step in the treatment process. We want it to move slowly enough, however, that the mineral material, sand, gravel, cinders, such things as that, to settle to the bottom of the tank and accumulate here. Now we have a constant means of removing this grit, which comes to us mostly when we have rainfall and water coming from the street, of course. We have a constant means of removing this grit. You'll see a bar of iron just above the surface of the liquid in this tank, and it's powered by a motor in the center and is rotating rather slowly. Fastened to that and extending clear to the bottom of the tank, some 3.5 feet below that, are scrapers. Scrapers are about so long, about that wide, and the first one in the center of the tank pushes this grit out a little ways from the center. The next rake picks that up, pushes it a little farther until the last one in line pushes it to the edge of the tank. And the edge of the tank is a good deal deeper than the rest of it. It's a pit, in other words, and this grit slides in the pit, accumulates here. Now extending down into the bottom of that pit is an inclined plane, like my arm is inclined here, something like that slope, about 3 feet above the top of the tank and clear down to the very bottom of this pit, some 3 or 4 feet below the surface of the liquid. And above that inclined plane is a rocker arm that's going to work like my arm is going to move now. Goes down a little ways and down and up and up, keeps repeating this motion. Fastened to that rocker arm a little piece of metal. About every 4 inches there's one of them. They're about so long, about that wide, and it's their purpose to bring the accumulated grit up this inclined plane. Take the first one, for instance, at the end of the rocker arm. As the rocker arm takes it down, it's at the bottom of the pit, and the rocker arm brings it up. It scrapes the accumulated material and brings it up this inclined plane a little ways. And then the rocker arm lifts it up, it goes back for another load, but the second rake and the 10th and the 20th and the 50th in line each progressively lift this grit just a little bit higher until it's about 3 feet above the top of the tank, and it drops into a hopper, and down below that hopper are little hopper cars that hold about 2 cubic yards of material, and these are on a railroad track. We can roll them out, pick them up with a truck, and haul it away as waste material, fill material. If a farmer has a gully, for instance, that needs filling, this is mineral material and is good fill material. After the liquid goes over the weir, liquid part, in the detritor, it goes to comminutors, C-O-M-M-I-N-U-T-O-R. A comminutor works a good deal like a food chopper. These are hollow cylinders that are about 30 inches in diameter and about 5 feet high. They're standing in a vertical position and they're rotating. They have slits, many of them, in the circumference that are about 1 foot long and about 3/8 of an inch wide. And as this rotates and the liquid comes up to these slits, any particle which is small enough will pass through the slit, get to the hollow center, and then can proceed to the next step in the purification. Any particle that's too large to get through this slit is held back. But on the surface of this rotating comminutor there are little knives. They will look to you like bright-headed screws, about the big as the end of my finger there. There'll be one up here, about 1 foot below that will be another one. You may see about 3 of them in line before you come to the water line. The housing, that's the fixed part in which this comminutor is rotating, has little grooves in it. And these little knives, as they go around, just fit in those grooves. So here's where our slicing action takes place. And we want this size reduction occurring so that later on, when we oxidize the impurities, we have more surface rather than to have the large pieces of material, most of which would be on the inside. So the comminutor is a size-reducing device. Next in line are the primary settling tanks. These tanks are some 4 times as long as this room, about twice as wide, about 14 feet in depth. Takes about an hour and a half for the liquid to move from the inlet end as the influent to the outlet end as the effluent of the primary tank. And in the hour and a half detention time, 2 things are taking place. Grease and oil, being less dense than the watery portion, rises to the surface, just comes up like a fishing cart would. We get grease from the home kitchens, from restaurants, from Marhofer's packing plant. We get oils from the various metalworking industries of Muncie, such as Warner Gear and Chevrolet, and perhaps other sources. Sometimes we get quite a lot of these. So this oil rises to the surface and forms a scum over the surface of the primary settling tanks. The organic waste, which was kept suspended in the detritor, now is rather quiet, settles down to the bottom, and forms a layer about 3 or 4 inches deep on the bottom of these tanks. Any heavy liquid in a plant like this we call a sludge. So this, since it is the first heavy liquid we handle, we call it the raw sludge. This is the material which would decompose and give offensive odors and be a health hazard. So we treat that elsewhere in the plant. On top of the primary tanks, you will see long planks that are just about as long as the tank is wide, have about 1 inch or so of clearance on either end. And those planks are about 6 to 8 inches in width and 2 to 3 inches in thickness, and they're standing on edge like this. Most of the plank is below the surface. If my left hand here represents that greasy layer that's on the surface of the primary tank, and my right hand represents this plank standing on edge, about 3/4 of it is below the surface and about 1/4 of it up above. It is fastened to an endless chain at either end, and that endless chain is powered by a motor so that the plank, which we'll call a rake, is pulled from the inlet end of the tank slowly down to the outlet end, and it simply skids ahead of it, this greasy layer. When the plank gets to the lower end of the tank, within some 3 feet of the lower end of it, the endless chain takes it right straight to the bottom of the tank, and then it begins scraping the bottom of the tank back toward the inlet end. And here is a pit that's a good deal deeper than the rest of the tank, and this raw sludge slides into that pit. Now there are a lot of these rakes. There's one about every 10 feet fastened to this endless chain, so one just follows after the other, keeps skimming off the grease and raking the raw sludge into the pit at the inlet end of the tank. We have a rather crude method of removing the grease and oil from the surface. It is simply taking a long pole with a piece of metal about so long on the end of it, about so wide, just looks like a big hoe, dipping it down below the surface of the grease and oil and giving a quick lift to it. There's a trough suspended at the lower end of the tank, about 2 feet deep and about 1 foot wide, and this greasy oily layer is lifted up above the top of the trough and falls into it. And when that trough gets about 2/3, 3/4 full of grease and oil and water, we get a lot of water with it, of course, it's pumped into tank wagons and hauled to the back end of the lot or wherever we have space to dispose of it as waste material. The water eventually evaporates, leaving the grease and oil, and that is eventually burned as waste material. The raw sludge, which has settled to the bottom of the primary tank, and we have about 100,000 gallons of that every 24 hours. It's about 6% solid, the rest of it is essentially water. So you see it is mostly water, some 94%. Here is a sample of the raw sludge which was collected by operators pumping the raw sludge to the digesters in the last 24 hours. Now, this has human excrement, it has disposal waste from the kitchen, it has industrial waste, it's got all those things, and perhaps some mineral material there also. It looks like it's higher in solid than the 6%, but that is a little bit foolish. Normally this is a little more of a brownish in color than what you see there. we pump this into digesters. We have two kinds of digesters, one called primary, the other secondary, and I'll differentiate between those later. It's pumped into primary digesters, which hold upwards of 1 million gallons. These primary digesters are simply huge cylindrical concrete tanks, about 20 feet in depth, with a floating cover. And the cover moves up or down depending on the amount of liquid that's on the inside. Well, we fill them with the sludge in the beginning, so there's no airspace between the cover and the tank proper. And that excludes any oxygen. Now, in the digesters, digestion takes place with anaerobic bacteria and without air, those which work in the absence of free oxygen. And anaerobic bacteria take what to us has been a waste product, either industrially or in the home, and use it as a food supply, and they grow and multiply. And as is true of us, we take in food supply, we give off waste products. These anaerobic bacteria are no exception. They take in food products and they give off waste products. And two of these are gases. One is carbon dioxide, the same gas that you are exhaling in the respiration process now. The other is methane, the chief constituent of natural gas. CH4 is the chemical formula for it. It's about 70% methane and 30% carbon dioxide. Well, natural gas is piped all the way from the Texas Panhandle up to Muncie and to Marion to Detroit and so on for the energy that it has in it. Well, we make better than 100,000 cubic feet of this mixed gas, which is 70% combustible material. So we ought to make use of that 100,000 cubic feet of combustible material to save energy so that we don't have to buy so much electricity. Now, this plant is not built just to make gas. It's built to take care of sewage and to treat it and render it impotent when the liquid part of it goes to the river. But if in the process we can get off a byproduct which can cheapen the process of purification, then we should take advantage of that, and we do of this gas. Now, we heat our buildings in the wintertime with this gas. We also have 3 diesel engines which burn either gas or oil, just like an automobile engine burns gasoline. They're constructed in much the same way. You have a cylinder and you have the combustible mixture mixed with air drawn in. You have a compression stroke. You have the mixture fired, and you have your power stroke. Now, your power stroke in an automobile engine turns the wheels and you roll down the highway. Here, our power stroke compresses air into a smaller space, some 16 million cubic feet of it in a 24-hour period, and this goes into our aeration process. So we make use of the energy content of this gas mixture to run our diesels when we have enough of it, and most of the time we have enough to run both of the diesels without buying very much oil. Since these digesters are outside concrete tanks, they would get very cold in wintertime, may even freeze and break. That would be disastrous. And then also, anaerobic bacteria have an optimum temperature of working. You people have an optimum temperature working. I don't know whether Dr. Hibbs has found it yet or not, but
Still looking.
Still looking. The optimum temperature for these anaerobic bacteria is somewhere between about 90 and 95 degrees Fahrenheit. So we try to keep them working for us under the best of conditions. So we heat the sludge that's in the digester, and we heat it much the same way that you heat water in the home. There you have water, cold water, going through a series of coils. And around these coils is burning some fuel, gas or oil or coal, and you transfer the heat of the fuel into the water that's in the coil, and then you have hot water in the bathroom or kitchen. Here we have big pipes and a pump that pumps the sludge out of the digester through coils around which is burning the gas that's being made in the digester, and circulating the liquid through these coils keeps the temperature in the digester, even in wintertime, up above 80 degrees and usually higher than that. If it drops down to about 60, these anaerobic bacteria act as if they're saying, you're not treating me right, we're just going to close up on you and not do anything. And that's about what happens. So your sludge goes into the digester and nothing happens to it, and as it comes out, it's about the same as the sludge that went in. So these anaerobic bacteria are very useful to us. Now, after about 30 days, you see we keep putting in 100,000 gallons of this raw sludge into the digester every 24 hours. We got to take off about 100,000 gallons to make room for this process, or build new digesters, new digesters, new digesters. And that wouldn't be economical. So after about 30 days, the sludge has been in the digester long enough that the anaerobic bacteria have consumed as much of it as a food supply as they can, and what is left is called digested sludge. They don't want to have anything more to do with it. So we pump that out of the primary digesters into secondary digesters. In the primary digester, the gassing action kept it all stirred up and mixed. In the secondary digesters, the gassing action is largely complete. It stays pretty quiet, and the solid settles down to the bottom, and that leaves a watery layer up above. And that watery layer we call supernatant. Super, above, natant, from the Latin verb meaning being born. So literally this is a liquid just being produced. Now that is black looking, but it doesn't have very high solid content. So we take the supernatant, let it come back through the wet well and back through the plant in the treatment process, let the solid settle out, and the liquid part goes to the river. That's by far the most economical way to treat the material that comes out of the digester if we don't get too much solid in it. Now, the bottom part has a high solid in it, and we can't put that back through our plant. We'd mess the whole thing up if we did. That is called digested sludge, and that is what we haul to the fields for its fertilizing value. We have 7 tank wagons, each of which holds 1,500 gallons. And if we take off, say, 40,000 gallons of supernatant today, to make room for 100,000 gallons of raw sludge in the digester, we've got to take out about 60,000 gallons of digested sludge. Now, since one tank wagon holds 1,500 gallons, you divide 1,500 into 60,000, you find it goes 40 times. We've got to haul normally about 40 loads of digested sludge away from the plant in order to keep those digesters free enough to keep them working the way they should work. Now we give this sludge free to farmers. It's about 7 to 8% solid, the rest of it water. Has about a half a ton of dry solids in each 1,500 gallon load. It's got a fair amount of nitrogen, a fair amount of phosphorus, pretty low in potash. Those are the 3 elements that are likely to be lacking in soil. When you buy a complete fertilizer, you always get all 3 of these. So we take it to farm fields that have no crops on them, like corn growing and so on. You can't drive across a cornfield, fertilize it, and destroy it by driving across with a truck. So we got to go when they are not using it for farming purposes. And then we're stymied sometimes by the fact that the weather conditions are such that we can't get in the fields. Too much rain, trucks slogged down, and spend all day getting one truck out of one field. So we have a bottleneck there with weather conditions of getting rid of the digested sludge, and that is one of the big problems that we have here. Now let's come back to the primary settling tank. We said we took the grease off the top and we took the raw sludge off of the bottom. And the main part of the liquid is in between. The bulk of that 14 feet of liquid is in between. I think I have a bottle standing around the corner there. If there was something in it, don't shake it, just pass it over to me. This is what you might call simulated sewage, made to look like sewage. We only get about 15 million gallons through here a day, so I have to make some up to look like sewage to show you. Well, this is permanent. I made this up years ago, and it's just as good tomorrow as it was yesterday as it was 5 years ago. This is oil, such as you use for lubricating an automobile. This is water out of the faucet, good drinking water when it was first put in. This is sand with a little bit of clay on it. This has stood quietly for some time, so we have a rather complete separation of solid on the bottom and oil on the top. If I agitate this, it'll look more nearly like the liquid that comes into the plant through the bar screen, through the pumps, through the detriter, through the comminutor, into the inlet end of the primary tank. And in the 2 hours, an hour and a half or so that it takes to go through the primary tank, we have this oil separating out, as I indicated, and we have the sand and clay representing the organic solids, the raw sludge settling to the bottom. Now, we can't build our tanks big enough and be economical about it to hold this liquid long enough so that it settles out and is as clear as you saw it before I agitated it. So in the hour and a half, we got most of the grease off. We got 40 to 50% maybe of the solid settling to the bottom, but there is still a lot of impure material in the center part of this. And that is what goes to the aeration tanks for aeration. There are 2 tubes back at you on the table there. Will you hand those up, please? One is covered with and one is not, about 3 inches in diameter. Right down at your hand. No, tubes, right at your right hand. That's right. These are called diffusion tubes. This is a shell, metal shell, stainless steel, fluted, little valleys in it, and about every 4 inches there's a row of holes about 1/8 of an inch in diameter around that. These are placed, several hundred of them, some 12 feet below the surface of the liquid in the aeration tanks. Here's where we put that compressed air that the diesels were compressing, something 16 million cubic feet in a day. And the air going into this, coming out these small openings, is broken up into little bubbles. That is still not good enough diffusion. So wrapped around that tube is a fiber, one of the modern plastics, saran. You use it in sheet form in the home, in the kitchen for wrapping foods. This is just a different form of it. This is tightly wound around that, so that the compressed air now not only comes out those little openings, but has to work its way between these tightly woven fibers, and that really breaks it up and makes practically all surface out of it. Now, if we had just one big bubble of air and put it through sewage, the only place where it would meet the sewage would be at the surface. If we break that up into smaller and smaller and smaller pieces, that's what the diffusion tube does, we're increasing the surface. And it's only where the air meets the sewage that oxidation of the impurities can take place. And in the aeration tanks, we make use of aerobic bacteria, those which work in the presence of free oxygen. The aerobic bacteria cause the oxygen which is coming in the compressed air through the diffusion tubes to combine with the organic material that comes through from the primary tank and oxidizes it and renders it impotent. After about 6 hours detention time in the aeration tank, the liquid spills over a weir and goes to the final settling tanks, sometimes called clarifiers. Here it stays about 2 hours, and in those 2 hours we have the solid settling to the bottom. These are circular tanks, deeper in the center than they are at the outside, about 15 feet deep at the center, and have a V-shaped bottom, in other words, and about 8-9 feet deep at the outer edge. There are scrapers that are scraping around the bottom of this tank, pushing the accumulated solids into the deeper central part of the V-shaped bottom. The liquid which reaches the outside of this tank is the effluent of the plant, and there is a weir, which is simply a dam, has V-shaped notches in it, and the liquid spills over these V-shaped notches into a channel that carries it to the river as the effluent of the plant. The solids which have settled to the bottom of the tank contain the aerobic bacteria. and we call that return sludge. So we pick it up with a pump and pump it back into the inlet end of the aeration tank, where the aerobic bacteria continue the oxidation process for another 6 hours, come to the clarifier, settle out in 2 hours, recirculate it so that we keep it continuously in action. That is really what gives this plant its name, activated sludge treatment plant. This is activated sludge. It's got the active aerobic bacteria on it, and by recirculating these from clarifier to aerator, we keep our process of oxidation going. I have a few samples on the table here. Samples are taken every 2 hours at different parts of the plant. Of course, the operators take samples. So this being raw sewage, there were 12 samples taken, and those 12 samples were mixed together, giving a composite sample. The last 24 hours, the raw sewage coming into the plant looked like this. The effluent from the primary tank, which corresponds to the center part of the stimulated sewage in the bottle, is in this jar. It has had the grease and a goodly part of the solids removed as raw sludge that has settled to the bottle. In the aerator, the liquid looks like this. The aerobic bacteria attach themselves to particles of matter as a whole. So on each one of these little brown particles there are hundreds of aerobic bacteria. And as they settle out, the aerobic bacteria settles with their home, you might say. This is where the active oxidation takes place. In the final settling tanks, the solid that you see from the aerator comes to the final settling tank, settles to the bottom, and this is the activated sludge which is pumped back along with the effluent from the primary tank. These two mix together so you can see why the liquid in the aerator looks something like this. Spilling over the V-shaped notches at the outside of the final settling tank is the effluent of the plant, and that is the liquid in the last 24 hours that I'm holding in my hand now. We're interested, of course, in a comparison between the polluted material as it comes into our plant, the raw sewage, and the effluent of the plant. Still polluted. We don't claim that this is drinkable, but normally it has better than 90% of the solid which settles out and of its demand for oxygen removed from it. And normally in this plant we remove 95 to 96% of the impurities that's in the liquid as it comes to us. What time do you want to?
Oh, it's at your convenience.
They have the rest of the afternoon, all night?
So we can get back at 3:45 probably.
3:45, okay. I might make a comparison between the liquid that you see in this jar and a product that you're very familiar with. How pure is ivory soap?
99.9%.
Well, that's pretty close. Let's see if we can come a little closer. You agree with him, well, you're both wrong a little bit. 44 hundredths, okay. 99.44. That leaves how much as an impurity? Let's see how good you are at subtraction. 56 hundredths of 1%. We're all agreed on that now, that if we have 99.44% pure, that would leave 0.56% impurity. Suppose I were to tell you that this jar contains 2/100ths of 1% of impurity. How does that compare with ivory soap? Ivory soap is 56 divided by 2 would be 28 times as polluted, wouldn't it? What is a polluted material in ivory soap, or maybe not polluted material, but the foreign material? Well, it's air that's been pumped in under pressure so that you can find that floating bar in that dirty water that you're taking a bath in. Or it's uncombined alkali or fat that goes into the making of the soap, or it's an adulterant that has been added or perhaps something that has been added for some specific purpose. We would say that ivory soap is a pure product, even though I'm telling you that it's 28 times as much impurity in it as has this raw sewage that comes into Muncie. You'd a lot rather take a bite of ivory soap and chew on it than a glass of this, wouldn't you? Wouldn't you? Yes, I would too. There's different kinds of pollution, we mean. One is non-harmful necessarily to us. I don't mean for you to go home now and get you a bar of ivory soap and go munching away on it and say that'll be your supper. But I do say that it wouldn't kill you. It might scare somebody. It might froth at the mouth and they might say you're mad. This whole plant, this plant costs some $5-6 million, I don't know. It's been built at different times and added on. And the sewers coming to it may cost $6-7 million more. Was built to take care of that relatively small amount of impurity. Small in percentage-wise, but very potent in its effect on life. Now, in my own lifetime, when I was in the elementary school and first studied physiology, I remember something like this, that the average expectancy was about 45 years. That is, a baby born had about the age 45 expect to die on an average basis. Today, that average expectancy is 70. It's been moved up 25 years in my own lifetime. Now, what has caused that increase in the livability, you might say, of the average individual? Well, certainly penicillin and streptomycin and the sulfa drugs and other modern drugs such as that have added to it. And certainly the better training of doctors, medicine, is a factor. And certainly better operative methods and better hospitals. But don't forget that the ordinary common plumber that you just take for granted has had a good part to play in this. Without the plumbing that you have in your home and the pipes leading to a plant such as this and the sanitary treatment of sewage such as we have here, we would still have these waterborne diseases and the epidemics, and our life expectancy would be considerably under 70. I'm not prepared to say how much it would be under 70, but we have a part to play in our purification of the liquid. You know, years ago, when the Indians lived in this area, the Delaware Indians in Delaware County along the Wapahani, Mississippi rivers, they didn't have the problem that we have today. They had a little village, but when things got smelling too bad, the squaws lifted the wigwams up, took them up a couple miles upstream, and they started all over again. That was easy. And when the Pilgrims and Puritans came over here, they had a house here, and 2 miles away was the nearest neighbor, and so on. They didn't have problems with waste material from human beings. But today, more than 60% of us live in villages, towns, and cities. And we live so close together, our waste products have to be taken care of by some process, septic tank maybe, or in most cases by a treatment plant that is something like the one that you're going to visit today. Now, this costs money. And when this plant was put into operation and people began paying sewage bills, they said, we never had to pay that before. Why do we have to pay it now? Well, it takes money to build a plant like this. Where are you going to get the money? You've got to get it through taxation, tax the people. Well, the people are the ones that are using the plant. So it was set up that a person using water, city water, would probably have that water ending up at this plant as polluted material, and they would pay a bill proportionate to the amount of fresh water which they used in their home, which is logical and fair in at least the majority of cases. It comes out about 2 cents a day per person as the amount of charge to the people of Muncie for the operation of this plant and for the payment of the bonds that were necessary to be sold to get the money to build the plant, to enlarge it, and to build the sewer facilities leading to it. I've rather hurriedly gone over the most essential steps in the purification of sewage as we have it in the city of Muncie. Do you have any question on any of the points that I have covered? Yes.
Do you have any occasion where the plant is poisoned, let's say some chemicals get into the sewage and you have the bacteria killed?
Yes. If we have acid released, and Indiana Steel and Wire a few years ago lost a whole carload of concentrated sulfuric acid. Some fellow turned the wrong valve and it went in the river instead of into their tank. Not in the river, it went in the sewer. And they called us up as soon as they found it out and said, we lost a whole carload of acid. What are you going to do about it down there? Well, we shut our gate ahead of the plant, let the sewage go to the river until we got a test that was non-acid, so that the acid coming through would eat our concrete tanks. It'd eat the sewer pipe out coming down to us, of course, but we couldn't do anything about that. But we could protect our tanks here, and we could protect our aerobic bacteria in the aeration tanks and our anaerobic bacteria in the digestion tanks. We sometimes get plating material, cyanides and chrome compounds, where you plate chrome and cadmium and so on. And these are injurious to the bacteria. They're not supposed to ever get that in our line. But once in a while we do get a shot of it. And if we get our aerobic bacteria killed in this aeration tank so that we can't recirculate them back and forth, we waste all of the solids that come out of the clarifying tanks. Instead of sending this back to the aerator, it goes back to the primary tank. The solids settle out and go to the digester, and then the liquid part of it goes to the aerator. And it takes about a week to 10 days before we again build up enough of the solid there and enough of aerobic bacteria so that this activated sludge process can continue satisfactorily. And we have to do that once in a while when we get septic conditions or we get poisonous material in the line. Now we have other problems here. We have the problem of oil and grease. Oil that's put out by the metalworking industries of Muncie and grease coming from packing plants in the home. You take one of these little particles now that should be in the aerator, that should be entirely free so that the aerobic bacteria are exposed to the polluted material in the sewage. As long as they can get at it and you give them oxygen, they're going to take care of that polluted material. Now suppose we have grease and oil. And grease and oil coats this little particle of material in which there are aerobic bacteria. Then you can bubble all the air through you want on the outside, and your bacteria are trapped on the inside of a greasy layer. So it doesn't work too good. And we have partially that condition today. This is not as good an effluent as we normally produce. I have my analysis finished on this, and this is about 87% pure compared with the first sample there, where it ought to be about 10% higher in purification, and that is due largely to grease and oil affecting our aerobic process. We have show you something about our industrial load. We have one industry in particular that gives us a tremendous load, and that's the Marhofer packing plant. They kill some 4,000 hogs a day, 5 days a week. Now I understand there are 5,000 students at Ball State this summer, so they kill about as many hogs in one day as there are students, and you've seen most of those students perhaps have meandered around and know that 5,000 means a good deal. One hog killed, the waste products from it give enough demand on a plant like this to be the equal of the waste products of 24 persons for one day. They kill about 400 to 500 cattle a day. And one cow kills, I used to say one cattle, but that just didn't sound right, so I got down to one cow or one steer. Is bigger than a hog, so it's equal to about 2.5 hogs. So 400 cattle would be equal to about 1,000 hogs. At 1,000 hogs equivalent to the 4,000 they kill, you got 5,000 hogs a day, 24 persons per hog. Multiply those together and you get 120,000. That would be what we would call the population equivalent. In other words, the waste products of this one industry is the equal, polluted material-wise, to a population of 120,000, and Muncie is 70,000 in population. Now they have a treatment plant, take out about 60% of this at the preliminary treatment process. We get the other 40%, which is about 40% of our total load at the plant here from one industry. And we have other industries. We get more polluted matter, more demand in our plant from industry than we do from the sanitary sewage of the homes. Other question?
Do you ever treat the effluent of any bacterial organisms as to make it more palatable?
No. Now,
Would it be possible?
yes and no. When we get some 15 million gallons of this into the plant a day, you can't expect to have a pure strain of any bacteria for any length of time because of this incoming liquid. So if you had a pure strain, you couldn't keep it. And it just so happens that normal sewage from the home, sanitary waste, contains enough of these anaerobic and aerobic bacteria that by concentrating them, by building them up in the plant, we have those things which will cause the degeneration of the material satisfactorily. Now they have trouble once in a while in starting up digesters, in getting them to gas properly. And we've had Dunkirk and Anderson come over and want to borrow some of our liquid out of the digester. Well, we're happy to give it to them. We give it to farmers, so we might as well give it to other people. That serves as a seed. You plant a pumpkin seed and you got a pumpkin growing up. Well, here are anaerobic bacteria inside of our digester. And if we take out 1,500 gallons and haul to some place where they don't have a satisfactory solution, we can seed that and get it started, and maybe it'll operate satisfactorily. Now, we don't have much trouble with our digesters from a standpoint of lack of digestion. Another question? Yes?
Does industry charge more because they have more?
Well, yes and no. I've worked for many, many years against Marhofer's packing plant. Had to, because I was the only one that knew the data, knew what load they were giving to us. And I suspect that some of the chiefs at Marhofer's packing plant would like to see Zetterberg just up and die, and their main problem would be taken care of. They were paying about $25,000 a year. And after some 10 years of intense effort, mostly on my part, it was doubled. They're still paying only about 1/4 as much as they should in comparison with the load which they're giving to us. Industries, like the home, pay on the basis of the water they take in. And if they give us an exceptionally heavy load, then they're not paying as much a proportionate share as those who are giving us less of a load. Now, most of the industries in Muncie are very, very nice. And Marhofer's is nice, I would say. We've got to have industry, and we've got to take care of their waste products. We've got to do all we can. But it's pretty hard to justify one industry taking up so much of our capacity.
Is there some other way to get rid of their waste products besides?
They would have to build a treatment plant somewhat similar to this and take what is their effluent now and treat it further, just like we treat it here, to render it less potent. They could do that, but it would cost maybe $1 million, $2 million. And they don't seem to have that kind of money to put into a waste product. They can put that kind of money into a nice sausage. I tell them that if they are just as proud of their sewage when it leaves their plant as they are of their sausage that they sell, then we'd be mighty happy out here. Another?
You suggested earlier that the treatment plant is not enough for all the sewage coming from town, and most of it is coming from industries. Would it be possible for industries, for example, to have some kind of minor treatment on the sewage before they let it in?
Yes, pre-treatment process. Now you take Delco Rini, builds, they have the capacity for building about 17,000 batteries for cars in a day's time. And they add sulfuric acid to that, and they charge it, and they pour out the spent acid. If they sent that spent acid to us, it would eat out the sewers before it ever got here. It'd eat our tanks up if it got here. It would kill our bacteria if it got here, and so on. So they buy sodium hydroxide in solution and neutralize the sulfuric acid, the acid part, and have a pH of something like 6.5 or so before it leaves the plant for the protection of the sewer line and the protection of this plant. So industries do cooperate, sometimes under duress.
What's the volume of sewage taken care of here per day?
It'll average about 15 million gallons. Now we have a tremendous fluctuation in flow. Along about 10 o'clock at night, the flow goes down from 10 o'clock at night till about 7 o'clock in the morning. Our flow might be such that it would only register, say, 7 million gallons if it kept up at that same rate for 24 hours. Right now, it would probably register about 18 to 19 million gallons. A plant like this has to be able to take care of fluctuations in flow. And when we have a little gentle rainstorm uptown, ours will jump up 20, 25, 30 million gallons here, almost immediately. Yes?
What is the difference between primary and secondary treatment?
Primary treatment is just the settling process. Anything that removes grit, maybe a head of it and so on, and the settling process, this is the primary treatment. Now anything that you do after this is called secondary treatment. That's the aeration and the final settling tank, and the digestion would be called secondary treatment.
Other questions?
Yes,
Yeah.
I'd like to know, detergents contain chemicals that are injurious and that do not dissolve or cannot be dissolved through this method of disposing.
The ABS type of detergent, alkyl benzene sulfonate, the first type that they have, is non-degradable in a plant like this. In other words, it largely goes through and out in the effluent. They have been working not on degradable ionic detergents. And right now, in England and France and so on, they're selling almost completely that line of work. In the United States, it's coming. We have some of it on the market now, but later part of this year, it'll probably all be that type. Now, we've never had much trouble here with detergents. Oh, I'd say never. I have seen our aeration tanks covered 5 to 6 feet deep with foam. Take a nice bubble bath. You took a dive into one of those. If you came along here on a windy day and the wind picked up that, and you were in the way, you got a nice bath too.
But is this all kept in suspension within the liquid, or is some of it
A
dropped?
froth or a foam that's on top of the liquid.
Well, is any of that taken with this material that you take to the farm ground, so that some of these chemicals are dispersed?
There would be some there, but most of it would leave with the soluble, it's soluble, and most of that would leave with the liquid part.
It stays in solution.
Most of our liquid goes out to the river. See, we have 15 million gallons a day coming in here, and only 100,000 gallons, that's 1/150th of what comes in goes to the digester. And some of that comes back through the plant, so only a relatively small portion of it ever gets to farm fields, and the detergents are soluble and they go to the river.
Okay.
Now, some places have had a lot of trouble. When they first gave samples of detergents, the ladies didn't know how to use them, and they used the same quantity that they had been using of soap in the past. They just about floated the sewage plants away. The sewage operators didn't know what was happening. Here was this sudden froth coming up, and they got to finding out that salesmen were going around handing out samples of detergents, and that the housewife was using 10 to 15, 20 times as much of it as she ought to use, and was creating this froth condition. I have to carry my solids higher in the aeration tank than I did years ago before we had detergents in the extent that we have now. If I didn't carry as high solids, I let these get down to about half,
then I'd get more fraud on these tanks. So that is somewhat controllable by the chemist. That's one of my jobs, is to keep that fraud on.
Other questions? Here's one in the back.
Yes.
The water and the sewage rate used to be the same in price. Now,
Pardon me?
water and the sewage
Yes.
bill. It used to be the same in Muncie.
Yes.
We heard the other day that the water bill is a little higher now.
Yes,
Everything's figured
that's right.
Right out here.
When the sewage bill was set up, they said we need so much money, and when they divided that up among the number of families that were serviced by this plant, it came out so close on a monthly basis to the water bill that they said, let's make it the same, then there won't be any squabble about it. Well, you get squawks anytime, so it doesn't make any difference what you do, but that's probably a little less. So originally, the water bill and the sewage bill was the same. Then we had an election coming along, and the mayor said the sewage bill's too high. If I get elected, we'll decrease the sewage bill. So partly on that basis, at least, he got elected. And to follow up his promise, he took 10% off of the sewage bill. If it had been $5, it was now $4.50. So that was a reduction. Then we built Prairie Creek, and Prairie Creek takes a lot of money invested, so the water company has to increase there. The sewage was not increased at the time the increase was put on the water. The water bill is about almost double, I think, what it used to be, and the sewage bill is a little less. So the average sewage bill, you pay sewage bill every 3 months, every quarter in Muncie, and for the average family, that will be about $6 for a quarter, or about $24, $25 for a year.
Did you did your analysis for today, what did you test for?
Test for solids. The amount of solids that we have in the liquid coming in any place throughout the plant is an important fact, and I can find out rather easily the difference between the incoming sewage and the outgoing on solids. An important test is the absorption of oxygen. That requires 5 days. It's called the 5-day BOD test. B for biochemical, O for oxygen, and D for demand. 5 days from now, I'll know how much air we ought to have been putting through today out in our areas. That's a funny thing, isn't it? But over a long period of time, that data becomes useful. And the 5-day BOD, or oxygen absorption test, is one of the most important tests to apply in a plant like this. And if we're covered with grease and oil, and they make a grease and oil analysis, make a graph sample someplace to find out where it's coming from. May want to know the pH, the acidity of it, and such things as that. I didn't go in detail on any of the individual tests because I didn't think it was a purpose. We didn't have the time anyhow. Is there another?
Any other questions? Well, thank you very much, Mr. Zederberg. I guess we're ready to look over the plant then.